Okay, so in this video, we're going to go over our types of intermolecular forces. So to start, we're going to compare our intermolecular forces with our intra-particle attractions or intra-particle forces that we've already discussed. So remember, we have our two categories. The ones that we've already talked about are intramolecular forces. These are bonds. So the actual attraction within a compound, your ionic or covalent bonds, what holds together the positively charged sodium ion with the negatively charged chlorine ion. That very strong bond, electrostatic attraction, the ionic bond, is an intramolecular, occurs within the compound. Similarly, our covalent bonds are the sharing of the electrons between atoms that have reasonably close electronegativity, and we can see that the sharing is either going to be equal or nonpolar or unequal polar. And both of these types of bonds are going to be significantly stronger than these intermolecular forces or intermolecular attractions that we're going to talk about in this video. So keep that in mind. In the hierarchy of strength, these are both going to be stronger than any of the IMFs, that's what I'll call them for short, that we're going to talk about. Intermolecular forces, or the IMFs, are just the attraction between neighboring molecules. So if we're talking about molecules, it's inherent that we're talking about covalently bonded compounds. Only covalently bonded compounds are called molecules. So we're talking about within the subset of covalently bonded things, what holds the compounds to their neighbor. Okay, so again, it's emphasis on the fact that we're talking about between neighboring molecules. So within the molecule itself, that's still covalent bonding. So we're talking about between. So in this little diagram that I've kind of sketched here, I have a covalently bonded water molecule, a covalently bonded water molecule, and a covalently bonded water molecule. It's these little red dashed lines that I've drawn in between the water molecules, which would be defined as intermolecular attractions. The bonds, the blue lines, are still covalent bonds. So if we look at just this particular set of compounds, the blue bonds are significantly stronger than the red dashed lines. Okay, these are just attractions. These are bonds. This is water. I gave this example the other day when we kind of previewed this in class, that if you think about water in all its forms, right? Solid as ice, liquid as water, gaseous as steam, we're going to see three distinct phase changes, but at no point does it stop being water. The thing that allows us to undergo those phase changes are these intermolecular attractions, right? But when water melts from ice to liquid, or water boils from liquid to gaseous, the water molecule, the H2O portion of this, still stays together, right? The covalent bond is not broken. The attraction is lengthened or shortened depending on what phase change we're doing. Okay, that's what we're talking about. So make sure you're keeping your eye on the ball here. We're not breaking any bonds. We're just lengthening or shortening attractions. Right? So these are weaker than our intramolecular forces. They are involved in phase changes, melting, freezing, boiling. And we have three different types. Okay, we have hydrogen bonds, dipole-dipole interactions, and London dispersion forces. And I will just go ahead and put it up front. I don't love that these are called hydrogen bonds. I think it puts the idea in your head that this is a bond like ionic and covalent, and that's just not the case. So I'm going to refer to them as hydrogen bonds because that's what they are accepted as, but it's not a bond. It's still just a really strong attraction. Okay? So of the three, the hydrogen bond is the strongest, and then the London dispersion force is the weakest. And the other important thing to know about these intermolecular forces is that their effect is cumulative. I can have more than one of these. And the more of them I have, the more energy is going to be required to complete one of these phase changes. So if I have all three of these, more energy will be required to melt, boil, or freeze. If I only have one of them, it's going to require less energy. So we're going to go through these kind of seemingly starting in an odd spot, starting at the middle. We're going to start with the dipole-dipole attraction and kind of work our way through. So the dipole-dipole attraction is the attraction between two polar molecules. Okay? Remember that polar molecules, number one, they can only exist in covalently bonded compounds. So only my non-metal bonded compounds. If there's a metal involved, you are in the wrong neck of the woods. Those would be ionic. They do not have any intermolecular forces. So the attraction between two polar molecules. Remember, when something is said to be polar, that means it has a partial negatively charged end and a partial positively charged end. The end that has more attraction to the electrons in the bond is going to be the partial negative end, and the end that has the less attraction to the electrons in the bond is going to be the partial positive end. Okay, so polar molecules have this unequal distribution. One side is negative, partial negative. One side is positive, partial positive. I'm stressing the fact that we're talking about these as being partially negative and partially positive because their attraction to other things is a lot less than something that is ionic that has full negative and full positive charges, right? When, just as an example, we make sodium chloride, the sodium becomes fully positive. The chlorine becomes fully negative. The fully positive and fully negative ions would attract each other much, much, much more strongly than something that's only partially negative or partially positive. Okay, so the fact that it's only a partial charge is really important. And remember, these little Greek letter deltas are how we mark the partial negative and partial positive charges. So we're going to look at an example. So here I have dihydrogen monosulfide, and we know because of the orientation of these molecules that in this bent shape with these unshared pairs of electrons on top, that these are polar molecules, that the sulfur end here is my partial negative end because having the unshared pairs means we're going to pull the electrons more that way, that the hydrogen ends are my partial positive ends. And when I have two polar molecules near each other, we're going to see an attraction between those molecules. Specifically, I'm going to see an attraction between the partially positive charged hydrogen and the partially negative charged sulfur. And that attraction there is my dipole-dipole interaction. So that's my dipole-dipole. Okay. And so when you have a sample of a substance, remember you've got tons of these. Think of it at a beaker, right? If I had this in a beaker, I'd have hundreds or thousands of dihydrogen monosulfide compounds in there, and each of them is going to be experiencing this dipole-dipole interaction. So having the dipole-dipole interaction holds them together, right? That means that a certain amount of energy is then required if I want to separate those two molecules. If I wanted to melt them, if this was a solid, right? I want to separate them. I want to lengthen this bond. I have to put energy in to stretch them. So when we talked about in the video the other day, the reason that things bond covalently, especially, is they want to reach that lower energy state. We saw it in a graph that kind of looked like this. And that this point here in the graph with the lowest energy was where we see the perfect bond length. Well, when things are bound, they have that low energy state. Well, if things are attracted, they're reaching a low energy state. If I want to separate that attraction, I'm going to have to add energy to it in order to separate them. Okay, so that's my dipole-dipole. I talked about this one first because the second one we're going to talk about, which is our hydrogen bonds, is a subset of dipole-dipole. Okay. So dipole-dipole is between two polar molecules. Hydrogen bonding is a special type of dipole-dipole. So it has to still be between two polar molecules, but we have some specific elements involved. So this is where I have a hydrogen on one polar molecule, and it's attracted to a fluorine, an oxygen, or a nitrogen on an adjacent polar molecule. Okay. It's those three elements in particular because those three are the most electronegative elements. So that means that their partial negative is going to be greater than anything else on the periodic table's partial negative. Those three have the greatest electronegativity, so they can pull the electrons more tightly than anything else, and it's going to have the best, greatest partial negative. Okay? So when I look for hydrogen bonding, I have to have a hydrogen attached to one of these on a different molecule being attracted to one of those on another molecule. Okay, so again, think about these are waters, obviously. If I've got a beaker of water, hundreds, thousands of these molecules in there, I have a polar partial negative on the oxygen, polar partial positive on the hydrogen, partial negative, partial positive, partial positive. So I have this attraction here between the hydrogen on water A and the oxygen on water B. And then water B could also be attracted to another water, and this one can be attracted to another water. I can have multiple hydrogen bonds forming here. And the important thing to note is not only is this a hydrogen bond, but it's also a dipole-dipole interaction. Remember, I said that they were cumulative. So you have two forces that are here, which makes that this interaction is a stronger interaction than this interaction. That the dipole-dipole and hydrogen bond together are going to require more energy to overcome than just the dipole-dipole alone. So the more forces we add, the more energy is required, the more they would resist a change of phase. Okay? And this should kind of just make intuitive life sense to you because everyone has boiled water at some point in your life, right? Everyone likes macaroni. Well, maybe not everyone, but let's just go with it. Everyone likes macaroni. When you want macaroni, the few minutes you're standing there waiting for water to boil seems like an incredibly long time. Well, it takes a while because I'm having to overcome not only the dipole-dipole attraction between my hydrogen bond, between my water molecules, but the hydrogen bond as well, and our last additional force we haven't even talked about yet, the London dispersion force. A tremendous amount of energy has to go in to get that water to boil because I have to interrupt all of these attractions to separate these molecules, which is why it takes forever to get the water to boil, which why it seems like it takes forever before you can eat your delicious macaroni. Okay? So the dipole-dipole, like we said, is the middle one. The hydrogen bond is the strongest of the three. Now, the last one we're going to talk about is the least strong attraction, and that is our London dispersion force. Okay, so let's take this a little chunk at a time. So London dispersion force, which we call LDFs for short, exists in all, emphasis, all covalent compounds. That means if it's polar, we have LDFs. And if it's nonpolar, we have the LDFs. So LDF is the only one that exists in nonpolar. Because remember, dipole-dipole and hydrogen bonding, you have to be polar to have those two forces. But London dispersion force, all covalent compounds, including the nonpolar, have them. And these are a function of the number of electrons something has. The more total electrons, the stronger the London dispersion force will be. Okay. So if I have something that has a just crap ton of electrons, it's going to have a really high London dispersion force. If I have something that has a really, really high London dispersion force because it has just an exceptional number of electrons, you might have more energy required to overcome those London dispersion force than you do a smaller molecule's dipole-dipole. So that's where things start to get a little bit tricky. You have to compare multiple factors, and I'll show you some examples of that here shortly. So this London dispersion force is based on the idea that electrons are constantly moving and can shift in response to neighboring molecules. And that's called being polarizable or polarizability, meaning I have something that doesn't necessarily have its own poles. It's not polar. It's in fact nonpolar. But because my electrons are constantly in motion, could we potentially have a time where in my molecule, let's see if my molecule is composed of atom A bonded to atom B, if my electrons are constantly moving around, shifting back and forth in the bond, could we possibly have a time if I were to like freeze frame it, more of them were by B and less were by A? And in that moment, if more of the electrons are by B and less are by A, wouldn't B be partially negative and A be partially positive? And then if I unfroze it and they continue to move around, could there not be another moment where more of them are by A and less of them are by B, and now A is partially negative and B is partially positive? Absolutely. That's what this is saying. And then if I had a neighboring molecule who also was having this occur, could molecule CD over here that I'm not drawing influence what's happening at the AB? Yes, absolutely. So what we're saying is that something that is nonpolar has the ability, because of the constantly moving, constantly shifting electrons, to have instantaneous moments where it is polar. That's what polarizability is. It's the ability to alter or influence the distribution of the electrons for just a minute to make really, really tiny, really weak partial negatives and partial positives for any one moment. And so because they're constantly shifting, the more electrons I have, the more this comes into play. Something with 200 electrons is going to have stronger London dispersion forces and stronger partial negatives and partial positives than something with only like 10 electrons, right? The force of 200 electrons is greater than the force of 10. So as the electrons shift, we'll see that we have those instantaneous dipole moments, partial negatives and partial positives for just a second. And we have these just tiny instant moments of attraction. That's what our London dispersion force is. So what we're going to do is we're going to compare the level of London dispersion force among two molecules. So we have C6H12O6, which if you remember from biology is our formula for glucose, with C2H4. So how do we calculate the number of electrons here? So I'm going to calculate my number of electrons by looking at how many electrons each atom has multiplied by the number of atoms. So I have 6 atoms of carbon, I have 12 atoms of hydrogen, and I have 6 atoms of oxygen. I look at the periodic table. Carbon has 6 electrons, so a total of 36 electrons there. Hydrogen has 1 electron, so a total of 12 electrons there. And then oxygen has 8 electrons, so a total of 48 electrons. So if I add all that up, we're looking at 96 electrons. So glucose has a total of 96 electrons. I'm going to compare that to C2H4, which if I'm remembering correctly is ethene. It might be ethane. I always get them confused. Carbon, 2. Hydrogen, 4. So carbon has 6 electrons, so that's 12. Hydrogen has 1 electron, so that's 4. And we're looking at a total of 16 electrons. So something with 96 electrons versus something with only 16 electrons, we're going to see a much higher London dispersion force from the 96 than we would the 16. Now remember, that's only one piece of the puzzle. We also would have to consider, are either of these polar, and if so, do they have also dipole-dipole attraction? Do they have also hydrogen bonding? Because remember, it's all cumulative. So that's what we're going to look at next, is how to figure out which forces are present in different compounds and then compare them. All right, so because intermolecular forces govern phase change, we can use the strengths of the intermolecular forces to make predictions about melting point and boiling point. So that's what we're going to do. That's our compare contrast exercise. So which substance has the higher melting point? Well, remember, higher melting point is just another way of saying who requires the most energy, right? Whose temperature do I have to raise the most in order to get it to change phase? Well, remember, adding heat is adding energy. I'm making the molecules move. So the one that requires the most heat change is going to be the one that has the highest melting point, is going to be the one that requires the highest amount of energy to overcome. So here's our first example. So we have BF3 and PF3. So the first thing I want to do with these is I want to ask myself the question, are these ionic or covalent? And then once I answer that question, if they're covalent, are they polar or nonpolar? Okay. So first question, are these ionic or covalent? Well, boron is a nonmetal, fluorine is a nonmetal, so this is covalent. Okay. Phosphorus is a nonmetal, fluorine is a nonmetal, so this is covalent. Okay. Had one of these been ionic, that would have been game over at that point, because remember that ionic compounds are held together really, really tightly and require a lot of energy, more so than our covalent ones, which are held together by our intermolecular forces. So ionic is going to win in the battle of melting point every time. But these are both covalent. So I need to now ask a second question. Is this polar or nonpolar? Well, BF3, boron, I know that that's going to make my trigonal planar shape. This is symmetrical, so I know that this is nonpolar. Okay. PF3, phosphorus makes my pyramidal shape. In my pyramidal shape with that unshared pair of electrons on the top, I know that this is polar. Okay. So now, how does this play into the intermolecular forces I have? Well, nonpolar compounds can only have London dispersion force. London dispersion force is going to be based on the number of electrons that I have. So when I look at boron, boron has 5 protons and 5 electrons, and fluorine has 9 protons and 9 electrons. So I have 9 electrons times 3, so 9 times 3 is what, 27, and then plus the 5 from the boron. So we have 32 total electrons. Okay. Now, with my PF3, it's polar. So I know that I'm going to have dipole-dipole. And then I have a chance to have hydrogen bonds because it's dipole-dipole. I have to look at the elements I have. Remember, to have hydrogen bonding, I have to have hydrogen, and I also have to have nitrogen, oxygen, or fluorine. Well, I have the fluorine here, but I don't have any hydrogen, so this does not have hydrogen bonding. But it does have London dispersion force, so I need to consider the London dispersion force. So fluorine, we know, has 9 electrons. 9 times 3 is still 27, plus phosphorus has 15, so 42 electrons. So now I'm going to compare my forces. Only London dispersion with 32, London dispersion with 42, and dipole-dipole. So which one of these is going to have a higher boiling point or melting point in this case? The PF3. Why? Because it has more cumulative forces. Dipole-dipole and London dispersion force, and this has more electrons, is going to make the London dispersion force even higher. So in this case, the PF3, because both of these forces act together. Okay, let's look at another one. So in this case, I have PH3 and I have NH3. So remember, first question, ionic or covalent? So non-metal, non-metal, this is covalent. Non-metal, non-metal, this is also covalent. Okay. What's my second question? Well, polar, non-polar. So I know with phosphorus in the middle, I've got that unshared pair of electrons on top. I know this is going to be polar. Now let's look at the nitrogen. Well, nitrogen is right above phosphorus, so it also has this unshared pair of electrons. So this is also polar. So that means if they're polar, I know automatically, oh, we have dipole-dipole. Now, do I have hydrogen bonds? I have the hydrogen, but no oxygen, nitrogen, or fluorine here, so no hydrogen bonding. I do have London dispersion force because it's covalent, so I need to think about how many electrons I have. So phosphorus has 15, and I have 3 hydrogens, each with 1, so that's a total of 18 electrons. Okay, now let's come over here. This is polar, so I know dipole-dipole. All right, hydrogen bonding. I have hydrogen and I have nitrogen. Now remember, it's not the hydrogen that's attached to the nitrogen in the compound. It's if I'm looking at, I'll draw it out real quick, 2 of these molecules next to each other, it's the hydrogen here attracted to the neighboring nitrogen, right? That's your attraction. That's your hydrogen bond. So this does have hydrogen bonding. And then London dispersion force. Okay. Nitrogen has 7 electrons plus the 3 from the 3 hydrogens. We're looking at 10 electrons. All right. So the pH 3 has us beat in terms of the number of electrons. So if this was the only force we were comparing, right, if I only had London dispersion or even London dispersion and only dipole-dipole, then the pH 3 would win because even though it's the weakest force, the London dispersion force is bigger. But what does this one have in addition to the dipole-dipole and London dispersion? It has the hydrogen bonding. And so the hydrogen bonding here is going to be what makes the difference. So NH3 is going to have a higher melting point because it has a greater cumulative force. Okay. All right, and we'll go on to our last example. So our last example, we have NaCl and we have H2O. So NaCl, ionic or covalent? Ooh, that's ionic. And H2O, oh, that's covalent. So ionic, remember, ionic doesn't have any intermolecular force. That ionic bond is strong. Winner, winner, chicken dinner, we're done. Ionic is going to beat covalent any day. Now, just for discussion, I am going to go through what forces we have here because it's good practice. But I already know, winner, done. This one's going to have a much, much higher melting point. Look at my covalent substance, my dihydrogen monoxide, my water. I know oxygen in the middle, 2 unshared pairs of electrons. This buddy is polar. I know that if it's polar, it has dipole-dipole. I know that because I've got a hydrogen and an oxygen, if I had another water molecule over here, the hydrogen would attract to the oxygen, so it has hydrogen bonding. And I know that it's going to have London dispersion force. Let's see how many electrons. So 8 plus 2, 10. Okay, so I know we have all these forces, but it doesn't matter because sodium chloride is ionic, and ionic is going to be stronger than covalent any day of the week. So when you're asked to compare something from like a phase change, boiling point, melting point, freezing point, you're always going to do what we just did here, which is take inventory of your intermolecular forces, compare them, see who has what, see how many electrons each one has, and remember that it's the cumulative force that makes the difference. Okay, just look at the total things that are acting, and remember that even though London dispersion force is the weakest force, sometimes that's the one that makes a difference. When all else is equal, check out that number of electrons and see if that's what's making the difference. Okay, hope that was helpful.